Oh, hi. Welcome everybody to our weekly lecture. Today, we are going to continue from where we stopped last week. But before we get started with our lecture today, one announcement regarding the upcoming exam. There will be an exam on Thursday. Our exam will be available within 24 hours. That means you have to complete within 24 hours. It does not mean you have to enter 24 hours, but it will be available. It will be available for only limited time, 24 hours. I'll send out today. The on the formula sheet, the equations, and any constant you may need so that you can print before Thursday. Please make an effort to get access to printer so that you can print the periodic table. You may use the same periodic table we used last time for quiz number 2. You will need the periodic table. I'll send out today this formula sheet which you will need for the exam on Thursday. More information will be posted on the announcement. Please be checking the announcement on the course on Canvas. So just so that you know, the exam will be on Thursday. If you have any question, please send me an email. If you encounter any problem during the exam, send me an email and I'll respond. What I want to do is kind of like go back to where we were or where we stopped last time, as far as the lecture is concerned. So there was an issue with quiz 2. Yes, Tierra, I received emails regarding quiz 2. Please send me an email, Tierra, and I'll respond to your questions. So Tierra, please send me an email. A couple of people there issue with quiz 2. Alternatively, if I cannot answer satisfactorily your questions on through email, you can schedule the Zoom conference, and I'll be able to help you out. So let's see if I'm trying to pair my whiteboard. Let me see if I can. Give me a minute. I'm trying to show you my whiteboard. All right. There we go. Yeah, I got it now. I wanted to set up my whiteboard so that we can continue from where we stop. If you just join in, I'll send more information regarding the upcoming exam. Let me share my screen. I want to show you. Can you see my screen? Can you see the screen, please? I don't want to, no, okay. I don't want to just, let's see, share the screen. You should be able to see the screen now. I don't want to continue. Make sure that we are on the same page. If you joined in last time, you should see, can you see my screen, please?
Yes, we can see.
Yes, thank you. So, this is the slide where we stopped last time on limiting and excess reagent. I explained to you what a limiting reactant is. A limiting reactant is a reagent which produce less amount of the desired product. Don't think that a limiting reagent is a reactant which is present in small amount. No, uh, in some cases that could be true, but that's not the best approach in identifying a limiting reactant. If you look at the PowerPoint slide here, this is the problem we solved last time in identifying or determining the limiting reagent. If given a awarded equation, you have to interpret the chemical formulas. The equation should be balanced so that you use the mole ratio. You know what mole ratio is from introduction to chemistry, even though it's not mentioned anyway in the problem, the coefficient in the balanced equation tells you, or you will use in determining the limiting reagent. For example, here is the zinc reacting with silver nitrate in aqueous form to produce silver and zinc nitrate, all right? You should be able to determine the molar masses of your compounds, or using the periodic table, use the periodic table to write down the atomic weight or atomic masses of element involved before you get started with the limiting reactant excess reagent problem. On my PowerPoint slide, this is what I solved last time in determining the limiting reagent problem A. Which one is the limiting reagent between zinc and silver nitrate? For every 1 mole, 2 moles are consumed. We are given the grams, and from the whiteboard here, the blue numbers here indicates the mole ratio, which we use in our calculation. So you start off by saying that if zinc or any other reagent is the limiting reagent, how much of the desired product will be produced? In this case, I'm using the zinc as the limiting as the desired product. Zinc is the desired product, and by all of the zinc used, this is the amount of silver producing 6.60 grams of silver. You do the same thing for silver nitrate. You look at silver nitrate. If silver nitrate, which is 2.50 grams, we are given the grams, you use the mole mass or atomic weight of silver of the silver nitrate. May be given, or you will be required to determine that mole ratio between silver nitrate and silver nitrate and silver. Atomic mass of silver 107.9, and then you do the calculation. The one which gives you less amount of the desired product is your limiting reagent. So you say therefore silver nitrate is the limiting reagent. Even though it was present in large amount, it gave us less amount of the desired product, that is the limiting reagent. And the amount produced by the limiting reagent, we call it theoretical yield. That is what you expect. We call this theoretical yield, what you expect to obtain from the limiting reactant. The amount you obtain from the limiting reagent is called theoretical yield. Along with this, you will see experimental yield. That's what you'll get from the experiment. Actual yield is the same as experiment. That is what you will actually obtain in the lab. But what you calculate from the limiting reagent is called the theoretical in theory. That's not possible in practical or in the lab. Now, let's see. I think we stopped at part D, explain or determining the excess reagent. We know zinc is, all right, we know zinc is the excess reagent. We know zinc is the excess reagent. I solved part C last time, but I wanted to solve part D, but we caught up with time. So how will we determine the excess reagent? If we know silver nitrate is the limiting reagent and all of the silver nitrate will be used, we write down the, we set up our equation this way, the amount of zinc we have, all right, amount of zinc we have is 2, this is 2.50 grams of silver nitrate. Use the molar mass of silver nitrate 169.87. All right, 1 mole of silver. This is silver. We want to cancel out this is grams of silver nitrate, NO3, all right, times 1 mole of thin silver nitrate, and silver nitrate will remain with silver. We want to know how many moles or how many grams of zinc will be consumed. Out of the 2 we have, not all of it will be consumed. We use the mole ratio. For every 2 moles of silver nitrate consumed, 1 mole of zinc is consumed. Look at the mole ratio I'm using because I want to cancel out silver nitrate here and silver nitrate down there. That's how you set it up. Times now the mass of silver zinc will be consumed. The mass which will be consumed is for every 1 mole of zinc, that is zinc, 65.39. This is grams of zinc. Zinc and zinc will go. Let's see how many grams of zinc will be consumed. What I'm doing here is when all 2.5 grams of silver nitrate are consumed, which is the limiting reagent, I want to know how many grams of zinc will be consumed because reaction will cease, will stop once the limiting reagent is consumed. So I'm just gonna multiply everything what I have at the top, 2.50 times 65.39, all right? I've multiplied everything at the top, divided by 169.87, all right, divided by 2, and I see this is how much will be consumed, 0.48, all right, 0.48 grams of zinc consumed. This is how much it is consumed. I see problems sometimes they ask you how much of the excess reagent will be consumed. So out of all right, out of what is consumed, what is left, how much excess reagent, excess will be given by the difference between what you started with minus 0.48. This is grams, this is gram of zinc, So 2.00 minus 0.48, this is what remain 1.5, 2 grams of zinc is in excess, This is how you determine the excess excess reagent. First of all, you start off with what? Start off with the amount of the limiting reagent converted to the number of moles, mole ratio between the excess reagent and the limiting reagent, and find the mass of the excess reagent consumed. All right, find the amount of excess reagent consumed, and then you subtract. Okay, and then you subtract. That's how you find or you determine the excess reagent remaining after the reaction is over. When you see this problem on the limiting reagent A, P, C, and D, it captures the whole picture on problems you will be tested on the limiting reagent. It's math space, and maths you have to practice. Okay, there's some concept you have to remember, like balancing the equation. Sometimes you may be expected to balance the equation fast before you do the limiting reagent problem, so be careful and know what you need to do. For example, all right, no one asks you here to determine the molar mass of each of these guys. You got to be able to understand that for a limiting reagent, excess reagent, those are the key things you should pay attention to. I had mentioned earlier on about the theoretical yield. Theoretical yield, okay, is the yield or the amount obtained from the limiting reactant. It is the maximum amount produced from the limiting reactant. And that is all what you need to do, or to remember that what is the amount you expect from the limiting reagent. That's the theoretical yield. Whereas actual is what you actually obtain in the lab, right? You have to wrap around your mind what is actual. Experimental is the same as actual, all right? Such word as this amount was obtained, all right? It was obtained. That means that is the actual, what you get from the experiment. These two terms, what you see on the PowerPoint slide here, the bolded terms here, you should know. Question on this theoretical yield and excess yield, will be what you understand. What is the theoretical yield? All right, Abby Simpson, will limiting reagent and excess reagent problem be on the exam? No. It will not be in there, Simpson. If you look at the study guide, it's up to just determining the limiting reagent and excess, but not up to you. Look at the study guide I talked about last time. I'm just going over this to kind of like jumpstart where we stop, and then we pick it up from there. But I remember we covered A and B last lecture, but not excess. That's why I'm showing you how to find or how to calculate excess reagent in a limit. There will be no question on. There will be no question on excess reagent. If there will be in there, if by mistake, okay? If by mistake there will be excess reagent, please send me screenshot and I'll give you points for that. If you see a question on determine the excess reagent, but there will be a question is what is limiting reagent? I covered that last time. I defined that. What is excess reagent? I covered that last time. So whatever we took today, for example, theoretical yield, excess, or actual yield, I know you know this. It's easy concept, but it will not be in the exam. Those two terms will be used in determining the percent yield. I know maybe in the lab, you have already used this equation, all right? You may have used this equation previously, or you may be about to use this equation on to determine the percent yield. of reaction, which is obtained by actual over theoretical times 100%. This is the amount you obtain in the lab. This is the amount you obtain from the limiting reagent. We will see an example on, and this is going to be in the next quiz, not this coming exam, all right? How do you determine the percent yield from a given reaction? If you look at this example, imagine you are working on ways to improve process by which iron ore containing 2 atoms of iron and 3 atoms of oxygen. This is iron 3 is converted into iron. Mole ratio is 1 to 3 to 2 to 3. If you start with 150 grams of iron 3 oxide as the limiting reagent, so we don't have to calculate the limiting reagent, what is the theoretical yield of iron? So we know, all right, the limiting reagent in this case, is iron 3 oxide. So I'm just gonna put iron 3 oxide here. Now it's the mass. We start with the mass here, which is 150 grams of iron, 150 grams of iron, to iron 3 oxide. What is the molar mass of iron 3 oxide? Somebody find for us. You know how to find real quick? Google out. Somebody Google out for us and keep me on the chat feature on the Zoom. What is the molar mass of iron 3 oxide? I want this to be interactive. Talk to me now. If you have your smartphone before you, you can Google out what is molar mass of Fe2O3. It will just give it to, yes, thank you, Kenneth. That is the molar mass of iron 3 oxide. It is 159.69. Look at how I'm setting up so that I'll cancel out the grams and grams. What I have here is 1 mole of iron 3 oxide. And the mole ratio between our desired product is 1 to 2. So I'm gonna have 1 mole here of iron 3 oxide for every 2 moles of what? 2 moles of iron. 2 moles of iron. I cancel that because of the space on my whiteboard. I'm just gonna write here. We want to know what is the mass, that is the theoretical yield. Iron, all right. I'm looking for my periodic table. So iron, atomic mass of iron here is 55 55.85 grams of iron, and this is 1 mole. This is the atomic mass of iron. So that mole and mole will go away. And let's see. You plug in your calculator, all right? This will give us the theoretical yield. 150 times 2 times 55.85, all right? Multiply everything at the top. Divided by everything at the bottom, which is 159.69. And that is all what I have in my denominator. And I see it is 104.9 grams of iron. Please look at the units. This is the theoretical yield in theory, okay? Maybe the student was trying to transfer, you know, maybe there was some flaws in the experimental design, and you know, the student didn't end up, or whoever is doing the experiment ended up getting the actual yield as 87. So if you want to find the percent yield in this case is given by actual over theoretical times 100% times 100%. So this is the actual 87 point what? 87.9 grams of 104.9 grams times 100% times 100% grams and grams. Show your work. All right, you got to show your work. You're taking the lab this semester and you'll use this equation, include the units, so that you cancel out, you'll remain with percent. So 87.9 divided by 104.9. And here I have times 183.8. This is 83.8 percent yield, which is good. This is a decent. This is a good percent yield. All right, anything 80% is decent. You will see this. You will see this equation. You will be using even beyond Chem1, even in organic 1, organic 2. You will synthesize your product and determine the percent yield. Some instructors or your instructor might ask you to explain why you didn't get the percent yield. Then you have to attribute to other factors. Any question on the percent yield? All right, let's move on. That is all what you need to know. This will not be in the exam, all right? The concept on percent yield will not be in the exam, but it will be in the upcoming quiz. I'll be giving you the study guide once I set the quiz, and you'll be able to do that. Any question on chapter 3? Yes, actual yield. How do you find actual yield? Anthony, how do you find the actual yield? You do not determine that. You always will be given, for most part, you will be given the actual. That is what you'll obtain in the lab anyway. All right. That is what you'll obtain in the lab. You'll be given that. For most part, you'll be given that. Do you know when the quiz for? I don't know right now, but my plan right now is once I'm done with the chapter, I'll give you, but if you, depending on how we progress with the lecture, I'll let you know. But my plan is once I'm done with a chapter, I will give you the quiz. So it's not going to be any time soon, depending on how we cover chapter 4. But once I'm done with that, I'll post the quiz for that. All right. Let me shift gears to chapter 4. All right. Shift gears to chapter 4, which is reaction in aqueous. Reaction in aqueous. And we know what a reaction is. We have balanced chemical reaction. All right. And you know what a chemical reaction is. It's chemical equation. Now, but what is new here probably is the term aqueous. Aqueous means a solution. All right. AQ, you have seen this, aqueous like that. Solution, all right. This is a solution where H2O is used as a solvent. All right, we're gonna talk about what this term is. You will see that in chapter, I think chapter 11 or 12 in Chem 2, solution, a solvent, a solution when you dissolve something. All right, when you dissolve something, you end up with a solution. And there are terms you need to know as far as the solution are concerned. Solution is made up of solvent plus what we call solute. I used to get confused when I was taking this course. What is what? Because all of them, they start with an S and S, like, SOSO. If you look at it, SOSO, you have to commit to your memory what each one means. Solution is when you combine a solvent and a solute. And this is the major component in a solution, major component. and this is minor, that is present in small amount. I don't want to dive that, but ours is to know what aqueous solution. So if you dissolve table salt, you end up with an aqueous solution. If I have Na, this is sodium chloride, all right, solid, you know what that means, and NaCl, and then I have an aqueous like that. Right away, you should know what AQ means. It means it has been dissolved. This is solid. This means it has been dissolved in H2O, all right? Water has been used to prepare the solution. So whatever we'll be talking about in chapter 4 is a solution where H2O has been used. This is the roadmap on what we will cover in chapter 4, general properties of aqueous solution, and I've underlined the word aqueous solution. And now you should know what aqueous solution is. We have used H2O as the solvent. H2O is used as a solvent. We're going to look at the precipitation reaction. I'll walk you through on how to determine the solid. You know, when you mix two reagents as solid forms, how will you know that this is the chemical formula of my solid? How will I know that this will not form a solid? I'm going to talk about that and show you the technique on how to determine the precipitate in a reaction. We will look at a special type of reaction, acid-base neutralization. It is one of the reaction you should know. Remember in chapter 3, we talked about the decomposition reaction. We talked about the combination reaction and combustion reaction. Those are the three reactions you should know. And then 4.3 is acid-base neutralization, and acid react with the base. We're going to talk about that. 4.4 is oxidation reduction reaction. This is when we will go back again to single replacement reaction. We're going to talk about single replacement reaction. These reactions are reactions where electrons are transferred. Look at the units of expressing the amount of solid particles in a solution, concentration in particular, molarity, and look at solution stoichiometry. So in short, that's the outline, chapter 4 outline. And let's start with 4.1. I just explained to you what an aqueous solution is. A solution is defined as a homogeneous mixture of two pure substances, yes, they form homogeneous mixtures. And solvent is present in large amount. I just gave you an illustration here. If you look at this illustration on the whiteboard, it separates, or you know, it gives you illustration on how to identify a solid and a solvent in a solution. It is present in small amount, large amount. Let's have acetone, for example, acetone, and then I can have H2O, all right, H2O, assuming that they blend in. If I have two samples, say A and B, here I have 10 ml, I have 90 ml here. Here I have 90 ml, and here I have what? I have 10 ml. From the constitution, you can see from the combination of solution A and B, you can identify the solvent. Solvent is present in small amount, all right? Small amount. Solvent is present in greatest amount. Solute is present in small amount. And it's not always two. You can have even more than two mixtures. All solutes, all other substances are solute. Aqueous solution are a solution where what? H2O has been used as the solvent. If a solvent is used to dissolve the solute, all right, to dissolve the solute, you end up with an aqueous solution. You end up with an aqueous solution. Quite often we think that, you know, solute tend to be a solid. No, it's not that way. You may think that always a solvent is a liquid substance to dissolve as, no. In some cases it's true, but it's not a one size fits all. Let me give you an example of a solution. Air, for example, air is a solution. It's an homogeneous mixture of several gases. There's oxygen, there's nitrogen, you know, it's a solution. Alloy is a mixture of two metals. An alloy, for example, bronze, is a solution. But in that case, you have a solid and you have a solid. You end up with the solution. All right. You can have liquid. When you talk about miscibility, you have two liquid blending into one another. For example, acetone and H2O. Does not mean that the other one is solid. Does not mean the other one is liquid. So be well-rounded in understanding the solute and solvent with respect to solution. So there are different ways of looking at aqueous solution. Let's shift gears to aqueous solution. And we'll go back to ionic compounds. Ionic compounds from the previous chapter, these are compounds made up of a metal and a non-metal, or a metal and a polyatomic ion. You know what polyatomic ions are. You should be able to recognize that this is a metal. If you don't know, you know, I'll give you the periodic table so that you say, oh, this is a metal, this is a non-metal, it's an ionic compound. All of them, they dissociate, all right, into ions. This is ionic compound. When this one dissociate, it will produce sodium ion and produce chloride ion. These are the ions which will be produced. I can have another, sample here, such as sodium, sodium hydroxide. For example, sodium hydroxide. All right, sodium hydroxide will produce N A positive, and then hydroxide. How do I know? It's not going to split into oxygen. It's not going to split into oxygen and hydrogen and the sodium. No, this illustrates how you should recognize polyatomic ion in a compound. I can have copper 2 sulfate, for example. It will not split into copper, into sulfur, into oxygen. No, it will ionize into copper 2 and sulfate. How do I know that? This is polyatomic ion sulfate? They expect you to remember from what I gave you. It is. I do have a couple of links in chapter 2 on polyatomic ion. So this is an ion, this is an ion. So all ionic compounds dissociate, and water surrounds the separated ions. Water surrounds separated ions. How does this come? If I have chloride, for example, here, and sodium, this is positively charged. Remember H2O, all right, H2O, it has positively charged terminal. Hydrogen, this is positively charged, and this is partially negative. So water molecules will surround what? Will surround the, all right, water molecule will surround the cation, the positively charged, using the partially negative terminal of water molecule. For chloride, all right, for chloride, if you look at the chloride, the partially positive H hydrogen there, if this is water molecule, hydrogens will be surrounding this because it is partially positive. So hydrogen, hydrogen, hydrogen. This is called the process by which, all right, the process by which water molecules surround separated ion we call hydration. It's getting hydrated. You have heard when somebody gets dehydrated, right? When you work out so hard, you get dehydrated, that means you're gonna lose water. To hydrate is to have the water molecule. So the process by which these water molecules surround the ions, we call it hydration. If it is a general solvent, we say solvation. This time right here, I hope you are writing your own notes. Solvation like that is the process by which solvent molecule surround solute particles, all right, solute particles. If it is a general term, solvation for a solvent, but if it is for H2O, we talk about the, all right, we talk about hydration is when specifically you're talking about water as a solvent. Now, molecular compounds such as sugar, when you put sugar in your coffee, it does not ionize, it does not dissociate. It does not dissociate. And there is a way you can tell, all right, for molecular substances which dissociate. If you look at the diagram below here on the PowerPoint slide, let me just expand this, make it. If you look at the illustration, the diagram here, figure, it shows sodium chloride in H2O. Once the sodium, which is purple, get dissociated from the crystal structure, it will get ion surrounded, all right, hydrated by water molecule. If you look at the orientation of water molecule, remember oxygen is red, so it's gonna surround. If you look at the chlorine, which is green, the orientation of water molecule is in such a way that water will get attracted, or hydrogen is attracted to the chlorine, whereas this one, oxygen, is attracted to sodium. That's how the solution is formed. If you shake until all these crystals disappear, you end up with a solution. Versus molecular compound, in the second diagram here, there is no ions, but it will just dissolve and form a molecule. It will not form a molecule. Now, those that is what happens when ionic compound is dissolved in H2O. That's what happens when a molecular compound is dissolved in H2O. Now, as far as ionic compounds are concerned, let me just put right here. Ionic compounds, compounds can either, these are strong electrolytes. What are electrolytes? Electrolytes are ionic compounds which dissociate, all right, which dissociates into ions and it conduct electricity. Let's put it this way. What is an electrolyte? An electrolyte is a substance which, when it dissociates in H2O, it conduct electricity from the word electricity, electro, all right? How will I know that? Is by the term ionic. All of them, they are strong electrolytes. Non-electrolytes, that means they don't conduct electricity. There's a diagram which we'll see in a moment showing the conduction of electricity. So a substance that when dissociate in water, it produces or it conduct electricity. Non-electrolytes, they do not conduct electricity. So in other words, all ionic compounds are electrolytes. So here, strong electrolytes, if an ionic compound dissociate, then it's safe to say that electrolytes, all right, electrolytes, strong electrolytes, ionic compound. Molecular compounds, electrolyte. Now, I know of, say, ionic compound, even strong acids are electrolytes, All right. Strong. We're gonna talk about strong acids. These are strong electrolytes. But for our case, we will only look at the ionic compounds. They dissociate to conduct electricity. So how will I know that this is an electrolyte? If it is an ionic compound, all ionic compounds have strong electrolytes. Weak electrolytes, they dissociate partially into to produce ions. Our question is, how will I know that this is a weak electrolyte? One is by memorizing their chemical formulas. This one, strong electrolytes, by recognizing that this is an ionic compound. Otherwise, it will be very difficult for you. You will just creating trouble if you try to make a list of all strong electrolytes. It doesn't work. That is a bad strategy for study. All I need to know is this an ionic compound? Yes. And then it's a strong electron. For a weak electrolyte, if it is not an ionic compound, then chances are it's a weak electrolyte. And these two terms, weak and strong, it has to do with the conduction of electricity. Sucrose, for example, that is sugar. If you dissolve sugar, if you have an electric circuit, it will not conduct electricity. The bulb will just remain dead. But if you have an ionic compound, not necessarily, okay, not necessarily table salt, all ionic compounds which dissociate into ions will conduct electricity. All right. There's some lab experiment where, it's designed in such a way that students are asked to identify whether unknown A is an electrolyte or unknown B is electrolyte, or this one is a strong electrolyte or weak electrolyte. Weak electrolyte, that means the bulb will just be dim. It will not be bright as you see here. So how will you know that? Unless you have that, and then I know that this is a weak electrolyte. Non-electrolyte will not conduct electricity, such as H2O. All right, such as H2O. Weak versus, all right, weak versus a strong. If you look here, this is not an ionic compound. You can say, well, I thought you say ionic compounds are strong electrolyte. Why are you giving me a molecular compound which is not an ionic compound, and yet you are saying it is an strong electrolyte? Look at my, my slide here. It can either be ionic compound or it can be a strong acid. Strong acid are those acids which ionize or dissociate completely to produce ion. H2 or hydrogen will be produced when HCl is dissolved in H2O and also conduct electricity. There are those which do not conduct electricity. We call those non-electrolyte. Weak electrolyte, acetic acid. All right, these are weak acids. All right, let me just give you acid. For example, here is a weak acid, hydrofluoric acid, weak electrolyte, carbonic acid, and this is the common one, acetic acid. This is the component in vinegar. All right, and I shall have aqueous, aqueous, aqueous. You should see in the, you should see if it is a strong acid, if it is a weak acid. So if I were you and I'm doing my master in chemistry in my lab and you are asked which one is a strong electrolyte, you may want to Google out the chemical formula and say, is this a weak weak acid? Then chances are, if it is a weak acid, then it is a weak electrolyte. You're gonna talk about chemical equilibrium later on in Chapter 15 of this course. Let's see. Here is an example on the classifying a compound as either strong electrolyte or weak electrolyte. You may not know, this is one way you can use elimination method. You may not know all these guys. Look, you may not know what they are, you may not know the names, you know, but if I have the periodic table, and I want to know if it's a strong electrolyte, that means it will conduct electricity, I will see which one has a metal and a non-metal. And the only one here is sodium hydroxide. I didn't have to memorize sodium hydroxide as a strong electrolyte for the bulb to glow, all right? This bulb glowing has to do with conduction of electricity, by the way. So how will I know which? Using elimination method, molecular compounds, some of them, they are weak electrolytes, but I know ionic compounds are strong electrolytes. Using the periodic table, I see sodium is a metal, and this is polyatomic ion. This guy right here, all these are non-metals. All these are non-metals. So this is the only one with a metal and a polyatomic ion. It is an ionic compound and stands out to be the only one which will cause the bulb to glow most brightly. So yes, they might glow, but it's gonna be dim. So strong electrolyte versus weak electrolyte, they might, you know, questions might come in any form. This question is on understanding the difference between strong electrolytes and weak electrolytes. Strong electrolytes and weak electrolytes. Please read more on that. What I'll do is I'm gonna send you more YouTube links on electrolyte versus strong electrolyte versus weak electrolytes. You can watch at your own time. All right, you can work at your own time. Any question? All right, let's shift gears to solubility of ionic compounds. Ionic compounds, we say that they dissociate, all right, they dissolve, but not all of them actually dissolve completely. I've seen, you know, most textbooks, most chemistry textbooks have 10 solubility rules they expect you to memorize so that you know, oh, this will dissolve, or there's solubility rules. Oh yeah, sodium hydroxide, thank you. Christian was asking, it's oversight on my end. What was the answer? Let me back up to this. Somebody is asking, what is the answer for this? It is sodium hydroxide because it is ionic compound. This is a molecular compound. They might, you know, the bulb might glow. The bulb might glow on this, but how will I know that this one will glow brightly? It is the only ionic compound, which means it will dissociate completely. So point here is identifying strong electrolytes. Strong electrolytes are ionic compound. Let's go to this table right here. You see this table? Ionic compounds, all right, all are strong electrolytes. That's why here we say B is the correct answer, sodium hydroxide, all right? So thank you, Santi, for pointing out that to him or her, sorry about that. Let's see, yeah, I was talking about the solubility rules here, solubility rules, and I was saying there are 10 of them. And when I look at this table, and when I look at the, all right, and when I look at the section in the text, it's kind of like too much information. I want to simplify in such a way that you will know the, all right, which one will be soluble, which one will be insoluble. The way it works is, all right, which one is soluble? Compounds containing nitrate. compounds containing acetate ion, all compounds containing chloride, except this, and this, and this, all compounds containing bromide, except this and this. I think that is too much work and you may not really recall, but I will allow you to use the, solubility chart, which I believe I had it somewhere. Let me see, I think it's hidden somewhere. I had solubility chart, which summarizes. Which summarizes the solubility rules. Let me show you where I have. It is available online, and I'll urge you also you print it out during the before the exam. I have it online. This is the solubility chart which summarizes the solubility rules. We'll blow it up so that we see how this works. If you look at this table right here, it summarizes what is soluble. In other words, let's see, you have the anions at the top right here. You have the cations on the first column, on the left column right here. When it form a compound, let's say for example, calcium and bromide, Ca2Pr, A cube means soluble, S means solid. So anything calcium, if I see solid, that means calcium. And you have to use the crossover rule, by the way, to write the correct formula. So calcium with hydroxide, it is insoluble. Calcium hydroxide, solid, insoluble. D means decomposition. That means, it will break down. You will not even see that, so it's not applicable. For most part, 90% of the time, this table really works well, and it's gonna help us down the line, all right? As far as the solubility rules, you will use these in the exam. I'll allow you to use the solubility chart so that you, instead of memorizing all this, you're gonna use that table. You're gonna use that table in our next, or in few minutes, we're gonna talk about the 3 types of equations. So I don't want you to just, you see, these are try to memorize all this. You will use the solubility chart, you're gonna print that. No, not for the upcoming exam, for future, for the quiz, I'll let you know. Anything I took today, no, nothing on chapter 4. Anthony, nothing on chapter 4 in the upcoming exam. So here is a question on solubility. So what dissolved species are present in the following solution? When it ionizes, you should see that there is, all right, there is not potassium chloride, but cyanide. It will ionize right here. It will produce potassium, which is a cation, and cyanide. Polyatomic ion cyanide. If you don't have any of those polyatomic ion sheet I posted online, please print. That is gonna help you, not in the exam, but probably in the homework assignment. Have before you polyatomic ion. There is a I gave more than 2 in chapter 2. So it is not going to be, somebody might say it's going to produce this. No. Wrong. You should see the polyatomic component, the monatomic cation. That's how I'm able to identify that, they expect you to be well-rounded in polyatomic ions. So the correct answer is D in this case. You may want to say, why can I get nitrogen? Why can I get carbon? Why can I get potassium? No, we don't split polyatomic ions, all right? We don't split polyatomic ions. Just like this, SO4 like that. This will produce potassium, and it will produce polyatomic ion sulfate. How do I know polyatomic ion sulfate? From chapter 2. Just away this one, let's see a common one. If I have sodium chloride like that, it's not going to give you, split chlorine and L. No, no, no. It's just going to give you sodium and chloride ion, sodium and chloride ion. That's how you see ions being produced when it dissolves. Question on the solubility. Before we look at chapter 2, question on solubility is, you'll see, and probably in the test, that in the next quiz or next test, that which one of the following is soluble. You have to use the solubility rules to solubility table I gave you to predict which one will be soluble. This table right here, I'll allow you in the next quiz, in the next test to use that. So that is the solubility rules. I'll allow you that will take care of that. Now let's see 4.2 precipitation reaction. A precipitation reaction is a reaction that produces a solid. I may have aqueous and produce C plus D. This might be in gas and this might be solid. This means solid will fall. It will fall mixed to reagent. A solid is produced. A solid is produced. All right. How will you know that this is a reaction or it will produce? It's by using that solubility table. It will help you in predicting which one is solid, which one is solid. For example, all right. For example, in this illustration, in this diagram, if you can, before I minimize, you may not see from where you are. Let me maximize this and I'll come back to this slide. If you look at this equation, I had to blow it up. If you look at this equation down here, look at my Kazakh, there is this compound, and this is going to produce potassium nitrate and lead 2 iodide. How do you know that this is a solid? How do you know that this is aqueous? This is aqueous. I'll walk you through on how you can identify which one is a solid. All right, which one is aqueous from this. It is by using the solubility table. So if this is lead 2, nitrate, lead 2 nitrate, NO3, like that, aqueous, plus potassium iodide, and this is aqueous. How will you know even the product? First of all, how do you know which one is the product? You should be well-rounded in looking at the polyatomic ion in the reagents where the ion will ionize, where it will produce the ions. Have a diagram and say, all right, I have a cartoon. You may want to use a cartoon similar to what I have here and say from the first reagent, I will uncross and take the 2. I'll take these 2. It's going to produce ion, lead 2 ion, sorry. And then the nitrate right here. Look at, I'm not saying 2. I'm not putting a 2 as a subscript for nitrate. It's just uncrossing over to get the ions. And for the second reagent, I have the cation first and anion second. You should see where the ions are. Look at the double replacement reaction. We're going to talk about double replacement reaction. They exchange the ions. In order to predict our product, they exchange the ions. So this one will combine with that, that one will combine with that, and these are our product. K, N, O, 3. Using what we learned previously, how to write the formula for any compound. 1 and 1 will cancel out. plus PPI2 using the crossover rule to write the correct formula. These two are my product. The two, this one and this one are my product. Where I have a question mark right here, I use the crossover rule, double replacement reaction. That's what's going on. You should be able to see where the ions are coming. The equation is not balanced. So if I have that, instead of rewriting it again, let me erase this right here and write the products. I'm gonna write the products on, it's no longer a question mark again, but we know what products are, all right? We know what products are. Here are my product. It's gonna produce lead, doesn't really matter which one is coming first, plus potassium nitrate. We still need to balance the equation. Matter cannot be created or destroyed. Before we look at the physical state, you see this one has aqueous. I'm gonna come back to that. The equation is balanced. You need to balance the equation here. There is a 2 in front of nitrate here. You need to balance the equation. We're done with that. The point here is, how do I know this? How do I know this? How do I know that? That is the physical state. The question mark is physical state. It is crucial in the next two concepts we're gonna look at. Use the solubility chart right here. Look at the solubility chart right here. Let me just minimize here. And if I look at the solubility chart, if lead 2 ion combined with iodide, will it form solid or aqueous? So I'm just gonna come back to my solubility chart. Look at where lead is, and look at where the iodide. Where you have the intersection right here, it is solid. Don't go with what is in the PowerPoint slide. So I know this is solid. So I'm just gonna make this solid right here. I'm just gonna make this solid. So I know that is solid. That's how I know it is solid. I didn't have to memorize. Given this solubility chart, I know it is solid. And then the other one, of course, will be nitrate. If you look at potassium and nitrate, you can, even though you may not really have, or group 1, look here, group 1. That means potassium is in group 1. Where is nitrate? Aqueous. So anything in group 1 will be aqueous. So this is aqueous. It may not be, all right, it may not be obvious, or you may not see on the solubility chart the element you are dealing with. You may use the group number. For example, magnesium, or remember the families of elements, they react the same way. That's how you can use that. So that's how you predict the physical state of your what? Of your product. So this is a precipitate. It will fall down. This is called PPT for precipitate. PPT for precipitate. So in section 4.2, you will use the solubility chart to predict the precipitate in your what? In your reaction, in your equation. And remember to balance the equation. Balance the equation first, and then you do what? You now use the solubility chart to predict the precipitate. I know why, because of what we're gonna look at it later. Balancing the equation, using the solubility chart to predict the precipitate in your solution. So it's not only limited to what you see on this slide right here. No, it is not only limited to what you see on the slide. So we're gonna use that and say, this is what it is. You have to know how to predict when you mix Look at table 4.1 on page 127. It's going to tell you what to do with that. When you combine this and that, let's say, for example, magnesium. Look at this. When magnesium and nitrate combine, what do you get? If I look at the chart right here, magnesium and hydroxide. Magnesium and hydroxide, this is hydroxide. I see it is solid, so I know it is solid. That's how you predict the solubility chart. Somebody is asking a question here. What did you say D stand for? D stand for decomposition. I think it doesn't stay. Like, as soon as it's formed, it's gone. There is a key here. I think it is right here. These are labeled D indicating decomposition. It breaks down. Look at the key. There's a term here. It gives you what indicates. Spaces label indicates no reference found. So no one will ask you anything with the dashes. So for most part, it's going to help you. So Anthony, D stand for decomposition. And it means you will not get that product anyway. It will not be part of the equation. And for most part, you will be asked something which you can predict a precipitate. Why will I expect you to have a precipitate in something which will decompose? So that's what I wanted to say as far as what D stands for. So, what I just did here is double replacement reaction is metathesis reaction, double replacement reaction. This is simply the double replacement, the exchange of ions. That means sodium will take nitrate and what? And magnesium will take hydroxide. So if you want to see metathesis reaction, you have magnesium, and please indicate the ions. And this is nitrate. I meant to say this is nitrate, NO, NO. And this is NaOH negative. This will help you in writing the correct formulas of your product on the other side. The correct formulas or product on the other side. So that's gonna be the metathesis reaction. How do I know after balancing? Chemical formulas, how will you know which one is which? Look at the diagram right here. I will recommend that use this diagram right here in order to write the correct formulas. Otherwise, memorizing the formulas will not work. It's the crossover rule will help you in writing the correct formulas. Once you switch the ions, you'll end up with the correct formulas of your product. For example, this will give me magnesium what? Hydroxide with a subscript 2 right there. Otherwise, somebody might end up just saying magnesium hydroxide like that. This is wrong. You can't do that. By looking at the ions, crossover rule gives you the correct formula, magnesium hydroxide. This is sodium, a positive one, a negative one will cancel, and I end up with that NaNO3. This is correct. That's how you write the correct formulas for your what? For your product. And then you balance the equation, of course, checking the solubility rules. Using the solubility chart, you should be able to see that this is solid. Look at the whiteboard. This is solid based on the solubility chart. This will be aqueous based on the solubility chart, and you end up with the correct balanced equation. You have stated what? The physical state of your reagent. That will take us to what? That will take us to the next concept where we are going is to write the molecular equation, the net ionic equation, and the complete ionic equation. Writing the 3 types of equation. All right, we have 3 types of equation of writing equation for double replacement reaction. Molecular equation is the one we have just been looking at, the balanced one. All right. For example, here, one here, molecular equation. It's just a regular balanced equation. For example, the one we looked earlier on, I'm just gonna use this to show you what total molecular equation. This is aqueous, and we added 2 in front there to produce lead-2, I2. This is 2. This is solid plus KNO3, and this is aqueous, and there was a 2 there. There is a 2 there. Now, this is molecular equation. This is molecular equation. It is a molecular equation. What this means, it is balanced, all right? It is balanced. Now, there is what we call complete or total ionic equation. Complete or total ionic equation. In complete right here, complete, sometimes we call this total ionic equation. Here, look, to generate this is you split aqueous compounds in molecular equation. Molecular equation. Do not split. Don't split what? Don't split gas. Don't split liquid. Don't split solid. You do not split those in complete ionic equation. And what that means is, in splitting, you should see where the ions are. For example, this one will split into lead-2 ion and nitrate. This one will split into potassium and iodide. And this one solid will remain the way it is, and this one will split. And remember, coefficient apply to everything. For example, the 2 here will apply across, the 2 here will apply across. The subscript right here will change to coefficient. Look at what I'll do in the second. This will be 2, this will be not 2, but I meant to say lead-2, and you have to write the physical state. This is lead-2, and then say aqueous, plus 2NO3 aqueous. I've changed the coefficient to the subscript to coefficient. I've changed the coefficient for nitrate here, and there is a negative there from the subscript. This was the subscript for nitrate in the chemical formula. This is 2 plus 2K positive, and you have to indicate the physical state, plus 2I aqueous. So the coefficient applied to both ions. Look at what I'm splitting. I will just leave alone, all right, I'll just leave alone the solid lead-2, all right, lead-2 iodide, this will be solid, plus 2K positive, plus 2NO3. And please indicate the physical state, aqueous, this is aqueous. If you look at this statement here, you have to split only the aqueous, and that's why it's important to write the physical state. Do not split solid, do not split liquid, do not split solid. When writing complete ionic equation, split the aqueous. Leave alone what? Gas, leave alone liquid, leave alone solid. This is what we call complete ionic equation. Complete ionic equation for this one, for this. This is molecular. It's just the balanced one. It's called molecular. But when I split the aqueous into ions, I end up with the complete ionic equation. Complete ionic equation. So this is number 2 here. This is equation 2. Now the last one here, the net ionic equation is 3 here, net ionic equation. How do I end up with net ionic equation? In order to do that, you do what? You cancel what we call spectator ions in the complete ionic equation. You have to cancel out. In order to generate the net ionic equation here, you cancel the spectator ions. You know, when you work over time, they show you on the paycheck that this is cross. And then they take the social security, maybe insurance or whatever. And then the net now is what you will get. So net is what will remain when we remove spectator ions. What are spectator ions? Spectator ions are ions which look exactly the same on either side of the reaction arrow. They are not the players in forming the solid anyway. Let me back up to the previous complete ionic equation. And I'm gonna circle spectator ions. Here is a spectator ion. Look at nitrate and the nitrate right here. They look exactly the same. We call that spectator ions. You have to balance. If I look at potassium and potassium, this is my reaction arrow, by the way. You got to look at where the reaction arrow is. This and this. The canceling, my point of reference is the reaction arrow. On the product side and on the reactant side, I cancel the spectator ions. They look alike on either side. And what will remain is the net ionic equation, So here is the net ionic equation. Lead to plus that. This is aqueous plus 2I negative aqueous to form lead to iodide, and this is solid. This is solid. So what you see in blue is the net ionic equation. Net ionic equation. Well, it's not always that you'll be asked in double replacement reaction what is a couple of there are so many form of question you can be given, you can be tested, you can be asked on these 3 concepts. For example, which one of the following is a spectator ion or spectator ion in the following? You should see that. Or what is the net ionic equation for this? You have to do that. Or you may be asked, which one of the following is the complete ionic equation for this reaction? So they are asking you for complete ionic equation or net ionic equation. I don't think, given the solubility chart and the given solubility chart and the periodic table, you should be able to answer question on double replacement reaction, precipitation reaction, in particular molecular equation, complete ionic equation, and net ionic equation. Things will be difficult if you don't know how to write the chemical formula using the crossover rule. If you do not, if you are not in a position to recognize polyatomic ion, all right. If you are not confident, or if you are not well-rounded in balancing the equation, this might also be a challenge. So please do not go back again and practice on those things we talked about, balancing the equation. So I've just explained to you molecular equation. It's just a balanced equation. For example, here you see all the time balanced equation. That is molecular equation. So to write the complete ionic equation, We will split these into nitrate ions, and there are two of them. 2 potassium and 2 chloride, it is aqueous. We will not split this. We will not split this. It is solid. We will split this to give us 2 potassiums and 2 nitrates. These 2 does not apply to sodium, to lead, all right? The only time is only these 2 came from lead, it's lead 2. So write the complete ionic equation, all right? Electrolytes. So we split that. We'll split the ions. So if you look at this complete ionic equation, we had to split the lead 2 nitrate. The 2 is coming from the subscript. So learn how the subscript changes to coefficient when you split. The subscript changes to coefficient when you split. The coefficient in the molecular applies to all ions in that compound. There was a coefficient of 2. And what appears on either side of the reaction arrow are called spectator ions. They are on either side of the reaction arrow. They are in the physical state, same physical state. We cross out, we cancel those. We cancel those spectator ions, and we end up with what? We end up with the complete ionic equation, complete ionic equation. So you can use a bottom approach and say, oh, I know what ions will appear in my net ionic equation. If you don't balance the molecular equation, it will not work out. So you cannot jump the queue. You have to start off from number 1, number 2, number 3, all right? 1, 2, and 3 in order to do it, in order to arrive at the net ionic equation, net ionic equation. Any question on double replacement reaction? You have to practice until you get it. Let's see. Which ions, if any, are spectator ions in the following? So if I look at the solid here, right, I don't have to, go all the way 9 yards and write the molecular equation and, complete ionic equation to see. All I have to see is which one is not. So silver ion and chloride ion shouldn't be there. So this is wrong, using elimination method, and this is wrong. Chloride, this is wrong, because it shouldn't form that. Yes, this one and this one, because I don't see it in solid. No ion, yeah, the correct answer is C. I didn't have to write the complete ionic equation to see which one is look alike on either side, but I'm using the precipitate. The precipitate came from ions. And anything outside the precipitate will be my spectator ions. So using the elimination method, the correct answer for this is what? It is C as in Jaws, sodium ion and nitrate ion. There are spectator ions for that case. Any question on net ionic equation, complete ionic equation? Any question? So remember, you will need the solubility chart. It's available online. That will help you in identifying the solid. If you don't know the solid, or if you don't write the physical state, you'll end up splitting what shouldn't be split. You will cross over what shouldn't be crossed over. For example, let me back up. If I don't indicate here as aqueous, solid, you have no knowledge which one will I split. But if I know that this is solid, it's very easy to know this is going to be my spectator ions. So bear in mind what it is. Now let's see. This is where we'll start stop, I'll stop at 4.3. We'll see how far we go on 4.3. That is acid and bases and acid-base neutralization. First, an acid right here. Let's define acid. This one is any substance that produce hydrogen ion when dissolved in it. It must have hydrogen and it must be aqueous. All right, HCl, aqueous is an acid. H nitric acid, this is nitric acid. Aqueous is an acid. So they produce H in H2O, produce hydrogen in H2O or when dissolved in water. Base right here, any substance that produce OH in H2O or when dissolved in water, And then neutralization reaction is a reaction between an acid and a base. So here is acid base neutralization like that. Reaction is a reaction where HA, this is an acid, react with a metal hydroxide to produce salt plus H2O. This is the criteria by which you know it is an acid base. Always water is produced in acid base neutralization, and this is ionic what? Ionic compound, a salt. We call that acid base neutralization. So you should know what an acid is, what a base is. It got two things. An acid has H in the chemical formula and it ionizes to produce hydrogen ion. Hydrogen ion, all right. We call this hydrogen ion. When produced in H2O, so hydrochloric acid, nitric acid, sulfuric acid. These are examples of common acid, weak acid, acetic acid. All these produces hydrogen ion well dissolved in water. You have to memorize, no, those bases also, bases ionizes, but in this case, they produce hydroxide. They produce hydroxide in H2O. Strong acid, they ionizes. You should know what strong acid, strong bases. So having said that, we have a strong acid. We have weak what? Weak acid. How will you know that? It's by memorizing, by the way. If you are required to take in your program Chem 2, in Chem 2, you'll be expected to remember what you learn in Chem 1. Strong acid, they completely ionizes in H2O. Examples are, to give you examples of this HCl, for example, nitric acid, example of strong acid. Weak acid, I gave you earlier on, and you should know their chemical formula, CH3, COOH, note their names. This is hydrochloric, hydrochloric, and this is nitric. Even sulfuric acid, no strong acid. Why do we say strong? They ionizes to produce hydrogen ion. This is hydrofluoric acid and acetic acid. This is called acetic acid, and they partially ionizes in H2O. So remember, strong acid versus strong bases. They have their chemical formulas and the names. Strong bases, group 1 metal hydroxide, they have OH in their chemical formula, all right? Weak electrolytes, they partially ionizes in H2O. Some of them molecular, you have to know their chemical formulas start with OH. They have hydrogen, but they do not produce, all right, they do not produce or generate electricity. All weak acids all weak acids do not ionize, all right? They do not conduct electricity in this case. So what I'll recommend in this case is, you know, use index card if need be, because that's the only way you can separate the weak acid and the strong acid, draw a parallel between them. This will help you when you are given a chemical equation and see the neutralization reaction. Remember the equation I gave you here, that an acid reacts with the base in acid-base neutralization to produce H2O and a salt. H2O, look at the slide, whiteboard, there is water as one of the products. And an ionic compound using the crossover, I don't know what is the chemical formula, metal hydroxide. It can be any metal hydroxide, and then you use the crossover rule to write the correct formula. This type of reaction is acid-base neutralization, where there is an acid and there is a base. So these are to the 4 types of reaction you should understand. There was combustion, there was decomposition, there was combination, and there is now acid-base neutralization, where an acid combine with or react with the base to form salt and H2O. I know this is an example of acid-base neutralization, because there is an acid, there is a base. Oh, well, I see it's now 12:29. I want to stop here for a minute and ask if there is any question. Remember, this will not be in the exam. As soon as I'm done with the lecture today, I will work on the formula sheet for our upcoming exam and any other information and any duration and what you need to do before Thursday. Question is, will the exam be given during the regular lecture? No. We will meet for our regular lecture, but I'll make the exam available from midnight to midnight. From midnight to midnight. That means very early in the morning on Thursday will be available. If you wake up 12:05 a.m. on Thursday before we meet at 10:50, the exam will still be available until midnight of the same day on Thursday. That way, you know, everybody will be accommodated. In case something happens, you still have time to. Please, we will meet before that on Thursday. If there is any question, you can send me an email. If you want one-on-one, I'll request you to join the Zoom. I'll schedule a Zoom session. Other than that, the class is dismissed. We will meet on Thursday again. Be on the lookout. There will be formula sheet posted this afternoon. Please make an effort to printing before Thursday. Thank you for coming in. See you on Thursday. Be safe.